Hello and welcome to the third week of the Markov chain topic. Last week when we learned about n-step probabilities, we have seen that as the number of n gets larger and larger, the probabilities are kind of stabilizing, which means that when the n is large, it doesn't matter where we are, in which state we are at this moment. When the n is very large, after n steps, the probability that we will be in a particular state is the same, regardless of where we are at this moment. So that's what we're going to talk about here, and that's why it is called steady state probabilities. So let's start. If you recall this table from the cola example, you can see that as the n grows from 1, 2, 3 up to 40, when n is large, like 40, the probability that a person will purchase cola 1 is 0.67. The probability that a person will purchase cola 2 is 0.33, regardless of whether he is currently buying cola 1 or cola 2. In other words, the matrices looks like this. So this is the matrix P. You can see that the effect of what he or she is buying right now is large, but then after 40 steps, you can see whether he or she buys cola 1 or cola 2. It doesn't really matter. Probability is 0.67 for cola 1 and 33 for cola 2. So here's the theorem. It says let P be the transition matrix for an S-state ergodic chain. Then there exists a vector of pi, which consists of pi 1, pi 2 up to pi s, such that when the n is large, when n is approaching infinity, you will have p to the power of n, or in other words, n-step probabilities that looks like this. You can notice that for the first column, the value is always the same, pi 1. For the second column is always pi 2. For the s column is always pi s. So it's really the same with our example here. It doesn't matter what the row is. It means that it doesn't matter where we are at this moment. The probability that we will be at a particular state is the same. So this column will always be pi 1, the other column pi 2 up to pi s. Okay, so that's the theorem, and notice that the keywords are first ergodic. That's why we're talking about ergodic chain last week. And then another word is keyword is that n is very large, approaching infinity. Now let's look at how we may find the values of the pi's. So from the theorem, let's look at this part. The theorem says that the probability of transitioning from state I to state j after n steps and then n is large equals pi j, right? As I said before, the state where we are, it doesn't matter anymore. So when you say transitioning from I to j, the I state doesn't matter anymore. So what you need to look at is just the state where you are going to. So from this theorem, it says that probability from I to j equals pi j. Now, n is already a very large number. So if you say, what is the probability of transitioning from I to j in n plus 1 step? Well, the answer is still the same, pi j. Because n is already large, when you say n plus 1, it's even larger, right? And so the result is still the same with this theorem, which says that the value is pi j. Now, from the definition of transition probability, if we want to define Pij in n plus 1 steps, we may break this n plus 1 into two parts, the n steps and then the 1 step. So we can say that if you want to go from I to j in n plus 1 steps, you can break it down like this. In n steps, you need to go from I to k. And k can be any state in your chain. So k can be from state 1 to state s. So you must go from I to k in n steps. So at the end of the step n, you are at state k. And then in the next one step, you go from k to j, right? Such that now you are at state j. So that's how we define the probability of transitioning from I to j in n plus 1 step. Now we combine these two points here to obtain that, okay, so pijn plus 1, we may replace it with pi j from the first point. And then also from the first point, you see that you can replace pik in n steps to just become pi k. And then the last part is still pkj. So now you have an equation saying that pi j equals to the sum of pi k for all possible k times probability of transitioning from k to j in one step. So that's for just one state j. If you want to compute the entire steady state probability for all states, you can use this formula, which pi is a vector and then p is a matrix. So pi is the steady state distribution vector. It is a row vector, and then each of the element is the pi, or steady state probabilities for state 1, state 2 up to state s. And then p is the transition probability matrix, or one-step transition probability. So if you multiply this pi times p, you will obtain pi. From the multiplication in the previous slide, pi equals pi times p. If you perform the multiplications, you will get s number of equations. However, if you solve this s number of equations, you will not obtain a unique solution, which means that you will not obtain a unique pi 1, pi 2 up to pi s. What you need to do, and this is very important, is that you need to replace any of the s equations that you obtained with this one. Pi 1, pi 2, the sum of pi 1, pi 2 up to pi s must equal 1. So from here, you obtain s number of equations, and then you just replace any one of them with the second one. Okay, and this is very important. So from the first part, you get s number of equations. You delete one of them or just throw away one of them, and then add the second equation. So finally, you will get s equations, and then you solve this final s equations. Now let's see the Kola example again. Given the transition probability matrix that looks like this, we are trying to obtain the steady state probabilities. So we get two equations from the multiplication, pi equals pi times p, and then remember that pi here represents a row vector that looks like this. We have two states here, so you only have pi 1, pi 2. If your problem, let's say, have 5 states, so pi vector contains pi 1, pi 2, pi 3, pi 4, and pi 5. Okay. So again, here pi represents a row vector, pi 1, pi 2, and p is the transition probability matrix. And then you perform the matrix multiplication such that you will get this equation that pi 1 equals 0.9 times pi 1 plus 0.2 pi 2, and then pi 2 here equals 0.1 times pi 1, 0.8 times pi 2. And then remember that you need to replace any of the equations with the equation that says the sum of all pi's equal 1. So here I just arbitrarily replace the second equation with this one. So your final equations look like this. The first one is from here, and then the second one is this. And then if you solve these two equations, you may obtain that pi1 equals 2/3 and pi2 equals 1/3. Good, so now you know that you may find the steady state probabilities using the equations pi equals pi times p, but remember that any one of them must be replaced by the equation that says the sum of all pi's equals 1. Okay, let me give you a question to check your understanding. To obtain the steady state probabilities of a system that has 3 states, what is the number of final equations that we solve? So as usual, I will give you the answer after the pause on the video. So if we have 3 states, it means that we have 3 equations from the relation pi equals pi times p. And then we replace any one of them with the equation that says the sum of all pi's equals 1. So in the end, we still have 3 equations to solve. Okay, in the next video, we are still going to talk about steady state probabilities, and then we are going to see how we may use these probabilities to make decisions. So see you on the next one. Thank you.